Bismillahirrahmanirrahim. Assalamualaikum. So today our team will be presenting about rolling process. Next. So meet the team. So our team leader is Muhammad Ashraf bin Muhammad Azlan. Our co-leader is Amirul Hakim bin Zulfaizal Fadilah. And the other members including me, Muhammad Daniel bin Makayam, Muhammad Yani bin Mat Yatim, and Zulus Niaspa bin Azman. Next. So this is our project content. So for chapter 1, introduction, chapter 2, SOP, chapter 3, plastic application, chapter 4, process problem, constraint and difficulty. Chapter 5, current and future application of plastic. Next, this is our table of content. Next, chapter 1, introduction. Rolling is a metal forming process in which metal stock is passed through a pair of rolls to reduce its thickness and increase its length. This process changes the microstructure of the material, making it stronger and more uniform. The rolling process can be performed at room temperature or with the use of heat. It is widely used in the production of steel, aluminium, and other metals, as well as in the manufacture of various industrial products such as pipes, bars, sheets, and more. The process can be classified into hot rolling, cold rolling, and other types depending on the temperature of the metals and the desired end product. Next. So for SOP, it is divided into two: SOP for hot rolling and cold rolling. So the both of the SOP are alike, but only one process different. So for preparation, check the specification of the raw material and the desired end product. Gather necessary tools and equipment. Set up the rolling mill. For setup, mount the rolls onto the rolling mill. Adjust the gap between the rolls to the correct dimension. Heat the rolls to the specified temperature. For rolling, load the raw materials into the mill. Start the mill and roll the material to the desired thickness. Monitor the process and make necessary adjustments. Next, for cooling, once the rolling is complete, cool the end product to room temperature. Remove the product from the mill. Next, next. So instead of cooling for cold rolling, the process is annealing. After rolling, anneal the end product to improve its ductility and formability. Heat the product to the specified temperature and hold it for a specified time. Cool the product to the room temperature. So for inspection, check the product for any defects or deviations from the specifications. Measure the thickness, width, and length of the product. For packaging, package the end product securely for transportation. Label the package with the product specification and weight. For maintenance, regularly inspect and maintain the rolling mills and tools. Clean and lubricate the equipment to extend its lifespan. For safety, follow all safety guidelines and procedures. Wear protective equipment such as glove, goggle, and hard hats. Keep the work area clear of any hazards. So we can proceed to chapter 3. Thank you.
Okay. Thank you to Mr. Daniel. In chapter 3, basically, me and my team members, which is Yani and Zo, we're gonna explain about the theory to practice, how plasticity theory is applied in the practical application. In the field of metalworking, plasticity theory is applied to the process of rolling to predict and understand the behavior of material during the rolling process. Plasticity theory is a branch of a continuum mechanic that deal with the deformation of material that exhibit plastic behavior, meaning they are capable of undergoing permanent deformation without breaking. When a material is rolled, it is subjected to the compressive force that cause it to deform plastically. The amount of deformation that occur in determined by a number of factors, including the thickness of material, the roll radius, the roll speed, and the properties of the material itself. The plasticity theory also can be used to model the behavior of the material during the rolling process, taking into account these various factors. For example, it can be used to predict the amount of reduction in the thickness that will occur, as well as the distribution of strain and stress in the material. Okay, next. So, in the rolling process, simple example of how plasticity theory is applied in the rolling process is the production of a steel sheet. The steel is heat at to a certain temperature, then pass through of a pair of roll with a certain radius. The plasticity theory can be used to predict the reduction in thickness of the steel, as well as the distribution of strain and stress in the material. The theory can also be used to optimize the process by determining the best radius, roll speed, and other parameter that will minimize the risk of cracking or breaking the steel while still achieving the desired level of reduction in thickness. Next. Okay, in the practical application of plastic theory in the rolling process, the plasticity theory is widely used in the design and the simulation of a rolling mile, as well as in the development of new material and the alloy that are better suited for rolling. The understanding of the material behavior during the process is essential in order to achieve high quality product with a minimal defect, and also to save energy and cost in the manufacturing process. So, in reality, the process of a rolling is a more complex and involve many different variables that have to be taken into account in order to achieve the desired outcome. But the basic principle remain the same. The plasticity theory is used to model the behavior of the material and optimize the process to achieve the best result. Okay. Now continue to Mr. Yani.
Uh, Thank you, Mr. Ashraf. Now I will proceed to the specify our work plastic deformation behavior. Now I will talk about the process of recrystallization. First, the work hardening. The process of work hardening is also known as the strain hardening. During this process, dislocation density is increased under recrystallization temperature of metal so that it becomes stronger and harder. There will be a pin down effect between discolation. This highly flawed microstructure will also prevent crack propagation as a result. The probability of rearrangement of metal and dislocations increases with increased temperature, resulting in lower strength and increased ductile. And then a recovery process involves the release of a portion of the internal energy stored within the microstructure prior to the recrystallization in a deformed material. The phenomenon normally occurs above the recrystallization temperature, where atomic mobility and derived diffusion are greatly facilitated. As temperature rise, diffusion increase rapidly and strain region tend to return to the original unstrained state. Now to the recrystallization stage. The recrystallization is a process in which new defect-free grains form in a deformed metal or plastic material. During plastic deformation, the original grains are subjected to stress, causing their internal structure to become distorted and the formation of defects such as dislocations. Recrystallization occurs when the stress and strain energy stored in the material exceed a certain threshold, causing the original grains to dissolve and new defect-free grains to form in their place. This process contributes to the refinement of the grain structure and can result in improved mechanical properties such as increased strength and ductility. Next, now we'll talk about the microstructure change when decrystallization. It is an important factor in determining the mechanical and corrosion resistance of a material is its morphology, which includes shape, size, and structure. The fact that all material consists of atoms arranged in short and long range order in regular or irregular patterns is well known. These solids are known as crystalline and nanocrystalline, respectively. There are two types of crystalline metals, those with single crystal and those with polycrystalline structure. Single crystal metals are the ones with body-centered cubic crystal, while polycrystalline metals are those with hexagonal closed crystal. Polycrystalline metals, on the other hand, consist of a collection of many small single crystals called grains. The grain boundaries separate the grains while maintaining the integrity of the metal. Furthermore, One grain contains several lots, with each lot containing a number of atoms. In terms of plastic deformation, it is known the dimension and shape of metal are permanently changed. However, in terms of microstructure change, only the density of the dislocation increase while the crystal structure, including the lattice parameter, are typically not altered. Uh, Now move on to Mr. Zul.
Okay, thank you, Mr. Yani. So I will explain about the residual stress on the rolling process. Residual stress has a lot to do with the strength of the rolls. So in compression and tensile, it is different. For compression, the residual stress will increase the fatigue strength, slows the spread of cracks, lowers shear stress at the surface of the roll barrel, and slow work hardening. And for the tensile, the residual stress may cause the roll breakage. However, if the over the cross section of the roll, the compression and the tension residual stress can cancel each other out. So in rolls, we need the right level of residual stresses to must keep in check in order to prevent it from failure. So next, I will pass to the next presenter.
All right, thank you, Zulsni. So moving on to chapter 4, which is process problems, constraint and difficulty. Next. All right, as mentioned as Mr. Mohammed Daniel, metal rolling is a process used to reduce the thickness of metal sheet or to shape it into specific form. The process involves passing the metal through a set of rollers which apply pressure and reduce the thickness of the metal. However, the process is not without its problem, constraint, and difficulty. So we have found out the two main drawback for this rolling process, which is surface defect and shape defect. Surface defect is in metal refer to imperfection on the surface of metal that can be affect the quality and the appearance of the final product. This can include scratches, cracks, uneven surface finish, roll marks, o-ring peel effect, and scallops. While shape defect is any imperfection in shape or form of a metal that can affect the quality or functionality of the final product. This can include non-uniform thickness, edge weights, edge waves, crossbow, center buckle, spiral buckling, and chamber. Next. And then we found two constraints for this rolling process, which is first the material cracking and then the maintenance and downtime. Next. So for the surface defect, we have scratches, which is a small linear marks on surface of the metal that can be caused by debris or dust on the surface of the before it's rolled, or worn roller that is not properly lubricated. While cracks are the small breaks or fissures on the surface of the metal that can be caused by high rolling loads, high rolling speed, or inefficient lubricant. Crack can also be caused by improper heating or cooling conditions. While uneven surface finish refers to a surface that is not smooth or consistent in appearance. This can be caused by improper roll alignment, uneven roll wear, or improper lubricant. Next. Roll marks. Roll marks is a mark left by a roller on the surface of the metal. This can be caused by a worn roller or by roller that is not properly aligned. Orange peel effect, as the name spoke for itself, this surface characterized by a rough or uneven surface that resembles the skin of an orange. It can be caused by uneven deformation of the material during rolling. Lastly, scallop. These are a small, shallow, concave shape deformation that occurs parallel to the rolling direction. It caused by the release of the residual stresses in the material. Next. For the shape defect, we have non-uniform thickness. So this shape defect characterized by uneven thickness of metal across its surface. It can be caused by improper roll alignment or uneven roll wear. And then we have edge wave. This edge wave defect characterized by a wave-like pattern along the edge of the metal. It can be caused by improper roll alignment, high rolling speed, or uneven roll wear. And then we have crossbow. Crossbow is characterized by a bow-like shape in a metal with center being higher or lower than the edge. It can be caused by improper roll alignment, high rolling speed, or uneven roll. Next. So then we have center buckle, spiring buckling, and chamber. Center buckle is a shape defect characterized by a bulging in the center of the metal. It can be caused by uneven roll and high rolling loads. While spiral buckling is a shape defect characterized by a spiring shape bulging in the metal. It can be caused by uneven roll wear or high rolling loads. Lastly, chamber. This is a shape characterized by a slight curvature across the width of the metal. It can be caused by uneven roll wear or high roll loads. Next to the constraint, we have metal cracking. Metal cracking is another problem that can occur during the metal rolling process. This can occur this can occur when the material is stretched beyond its elastic limit. This can be caused by high rolling loads, high rolling speeds, or insufficient lubrication. For example, if the rolling loads are too high, the metal may be stretched beyond its elastic limit, leading to cracking or another material defect. Similarly, if the rolling speed is too high, the metal may not have enough time to properly deform, leading to cracking or other material defects. Rolling wear is another problem that can occur during the metal rolling process. This can occur due to the constant contact between the roller and the metal. Roll wear can cause shape defects and also lead to increased energy consumption. For example, if the roller are worn, they may sorry uh, up to the previous page. Sorry. For example, if the roller are worn, they may not apply consistent pressure to the metal, leading to uneven thickness or other shape defects. Additionally, worn rollers can also increase energy consumption as they may require more power to turn and apply pressure to the metal. So lastly, we have maintenance and downtime. Maintenance and downtime are also major constraints in the metal rolling process. Regularly, maintenance is necessary to keep the rollers in good condition and to prevent defects from occurring. Downtime can be costly and can lead to production delays. For example, if the roller needs to be replaced, the rolling process must be halted, leading to the downtime and lost production. Safety is a major concern in metal rolling process. Metal rolling can be dangerous and require proper training and safety procedure to be in place. For example, if proper safety procedure are not in place, workers may be at risk of injury from moving equipment or hot metal. Moving on to chapter 5, which is explaining the current, advanced, and future technology in plasticity application. Next. So for the current technology of metal rolling in plasticity application is based on traditional techniques that have been used for centuries. The process typically involves the use of a set of rollers that used to compress and shape the metal material. The rollers are typically made of steel and are powered by electrical or hydraulic metal. The material is fed into the rollers and is compressed and shaped through the use of different rollers with varying diameters. The rollers are adjusted to apply the desired amount of pressure to achieve the desired shape of size. And then we have advanced technology. So one of the most advanced technology currently used in metal rolling is the use of computer control rollers. This technology allows for greater precision and control of the rolling process, as the rollers can be programmed to apply specific amounts of pressure and to achieve specific dimension. Computer controllers are allowed to use the material with varying properties, such as different hardness level, to be rolled with greater precision and control. Another advanced technology currently in use in metal rolling is the use of high temperature rolling. This technique involves the use of rolls that are heated to high temperature, which allow the rolling of material that would otherwise be too difficult to roll at lower temperature. High temperature rolling is particularly useful in the production of material with higher melting points such as titanium and nickel alloy. So in the future, we are we can expect to see more advanced technology being developed and implemented in metal rolling. One such technology that is being researched is the use of ultrasonic rolling. This technique involves the use of ultrasonic waves to create high frequency vibration that can be applied to metal material during the rolling process. This can help to reduce the amount of force needed to roll the material, which can result in greater precision and control over the process. Another technology that is being researched is the use of nanotech in the metal rolling. This involves the use of material and the techniques at nanoscale to improve the properties of the material being rolled. For example, researchers are looking in a way to use nanoparticles to improve the strength, ductility, and the toughness of the material being rolled. So to cut it to the chase and to sum up all the uh, presentation, metal rolling is an essential technique in plasticity application of metal. The current technology of metal rolling is based on traditional technique that be used for centuries, but advanced technologies such as computer control and high temperature rolling are now being used to achieve greater precision and control. And in the future, we can expect to see more advanced technology being developed and implemented to metal, such as ultrasonic and nanotechnology. I think that's all from us. Thank you.